Great. So good morning, everyone. Today we're going to do lecture 13, a lucky number. We're going to do the post-correspondence problem, which is a long reduction, but then we're going to use it to show that the validity problem for first order logic is undecidable. So here goes. So the post-correspondence problem, I put notes like this on the website. You should be able to read them and access them. And of course, details and all are there if I skip over anything in class. So what's the post-correspondence problem? It's a typical matching kind of problem, which seems to have nothing to do with computation or Turing machines or anything like that. Yet, surprisingly, you can solve the halting problem for Turing machines if you can solve the post-correspondence problem. So the halting problem can be reduced to the post-correspondence problem, and we are going to do that reduction explicitly. So let me tell you what the problem is. You're given a finite set of pairs of strings. Okay, so let's write this set in this form: alpha 1, beta 1, alpha 2, beta 2, and so on. So the way you should think about these strings is kind of like domino tiles. So I will draw them like that. So you've got a domino with alpha 1 written on top and beta 1 written below. You've got another one with alpha 2 written on top and beta 2 written below. And you have as many as you want of each type. So this is not just telling you that I've got k dominoes. It tells you I have k types of dominoes, and for each type I have as many as you want, an arbitrary number if you wish. And what we're going to do now is ask the following question. Can I put a sequence of dominoes together, or let me call them tiles, such that the concatenated string on top is the same as the concatenated string below. Okay, so simple matching problem. It looks like you're given it looks like a simple children's game. Maybe you have these tiles and you want to see if there's some arrangement whereby you can get the same string on top and on the bottom. Obviously, all the alpha i's are different from the beta i's. Otherwise, if there's a tile with the same alpha and beta on top and bottom, you just take that one and say, there, done. Okay, because I've got one domino with the same string on. So the interesting examples are when the string on top and the string on the bottom is never the same, yet perhaps there's some combination that can be made to match. So here's an example. So I'm going to write this domino types as little tiles like this. So one type has B on the top and B, B, B on the bottom. And then the other one looks like this. It has 5 things on top and only 2 on the bottom. And the last one looks like this. It has BA on top and just A on the bottom. So you have three types of dominoes, but of course, I want to emphasize it's three types, not three dominoes. Okay, I have as many as I want of each type. Okay, so this is an example of the post correspondence problem. So that's what we call it, the post correspondence problem, PCP. Okay, so solving the problem means finding exactly such a sequence of tiles. So a solution to this instance of PCP is a sequence of integers or let me say positive integers that describe a match. So we label the first one, this is type 1, this is type 2, this is type 3. And now, what's an example of a solution? 2, 1, 1, 3 is a solution. And why is that? Well, if I take domino number 2, I've got B, A, B, B, B on top and B, A on the bottom. Okay, I'll write the 2 in the middle to remind you this is a domino of type 2. Then it says take 2 copies of 1. So 1 just has a B on top and BBB on the bottom. You can say, oh, that's pretty good. My BABBB matches the BABBB there, but of course there's a B here. So then you put another type 1 tile. So now I've got unmatched BB on top, BBB on the bottom, and a type 3 tile has exactly what I need. It's got an extra B on top. Okay, so if you look at the top string, it's B, A, B, B, how many? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and then an A. And if you look at the string on the bottom, it's B, A, B, 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 A. These strings are the same. Okay, so that's it. I give you these tiles, finite set. I specify a finite set of tile types, and then I ask you, I can use tile number 1 37 times in a row if I want. I can put it here, there, everywhere. I can put any tiles in any order. I have as many as I want of each type, but only those types. I can't cook up new tiles to make them match. So is the problem statement clear? Again, it looks like a combinatorial, one of those combinatorial puzzles that you can write a computer program to search through and find, but actually this is an undecidable problem. And it's pretty amazing that such a simple thing should be undecidable. Okay, so of course, just because I write down a post correspondence problem instance doesn't mean there is a solution. Maybe some of them have no solutions whatsoever. So for example, here is another instance of PCP. So I will say, perhaps casually, we're solving PCP. What I really mean is we're solving an instance of PCP. Certainly for specific examples, you can solve them. Just like for specific programs, you can see that they halt. What we cannot do is find a general algorithm that always solves the question. Okay, so here's an example. And what do we have here? 3 kinds of tiles. And this has no solution. Why? Why can you instantly look at this and say, no, that's impossible?
Adam says the bottom is longer than the top.
Right. Every string on the bottom is longer than the top. No matter what dominoes you put together, the bottom string is going to be longer than the top string. There's no way they can be matched. Okay, so that's an easy way to tell. The point is we want an algorithm that can examine anything and say, yes, this is solvable, and here's the solution, or this is not solvable. So, theorem.
Do we always assume that the strings on the tiles are not empty?
Yes. I don't think it makes a big difference to the problem, though. Certainly for the one I'm going to do, everything is non-empty. But anyway, Post's theorem, it is undecidable. Whether a given post system has a solution. Okay, and the proof will take us until the break, or to be precise, we'll have a break when we finish this proof. Right. So let me tell you the idea. What we're going to do is you take a Turing machine and a word. So we're going to solve the acceptance problem. Take a Turing machine and a word, and we're going to effectively construct an example, or rather an instance of PCP in such a way that that PCP has a solution if and only if the Turing machine has an accepting run on that word. Right, if and only if the Turing machine has an accepting run. So if you can solve the post correspondence problem, you can solve the acceptance problem for Turing machines. This is a known undecidable problem. Okay, so given a Turing machine M and an input word W for M, we will design S. So S is our finite family of tile types, such that S has a solution if and only if valcomps MW is not empty. So that's the idea. So the whole question now it's all just details on how I designed my tiles. Okay, that's a bit of fun. Not so absolutely crucial that every minuscule detail is followed in real time, but this general plan is, you must understand, this is what we're trying to do. Okay, so first, temporary restriction. We will label one of the tiles as the start tile. and insist that you must start with that tile. Now, this is obviously not the post correspondence problem anymore. It's a restricted thing. Okay, it'll just make it easier for us to design the tiles, but it's simply not classic PCP anymore. It's a modified version. But at the end, we'll show you that this modification was only temporary and just for the convenience of presentation. Otherwise, I've just presented it and you'll wonder where the heck did all these weird symbols come from and what role do they play? So I'm going to describe this in two phases. First, we'll do it for this restricted version of the post correspondence problem, where there's a designated start tile and you must start with that tile. And later on, we will redesign the tiles with some extra symbols that will force you to do that anyway. Okay, so generic PCP is indeed, sorry, the acceptance problem can be reduced to generic PCP. Okay, good. Let's design tiles. Okay, so we'll label the start tile. So the start tile, I'm going to insist, looks like this. So what we're going to do, just as we did valcomps yesterday, we're going to show successive configurations of the Turing machine, right? Successive configurations of the Turing machine, and each configuration, there'll be a special hash mark symbol to separate it. This means this configuration is finished. Now I'm describing the next one. So it's got to be a valcomps in the sense of what I talked about yesterday, a valid computation. And the way we're going to design the tiles is as you put them together, you will be forced to go from one configuration to the next according to the rules of the Turing machine. And the cleverness in doing that is in the design of the tiles. So the start tile, we're going to say you have to use this tile to start. Q0 is the start state of the Turing machine. And your initial word is W. Let's say the letters are W0, W1, all the way up to WN. Okay, so that's the start tile. It has to look like that. And what do you see on the bottom? The start configuration of the Turing machine. On top, just the hash mark. Okay, so if you're going to get any kind of match, you also have to produce this thing on top. And so we're going to give you some tiles that will allow you to do that. But the cleverness of the design is that as you try to complete the matching of this with a corresponding string on the top, you will also be putting on the bottom the next configuration. And then it'll be set up to do the next step of the computation. And when you finally complete the match, my God, you'll have a valid computation. And if you can't complete the match, it means there's no valid computation. Okay, so after that, this is now just all details. So for every transition of the form, so we have transitions that tell you if you're in a state Q and you're reading the symbol A, then you change the state to from Q to R, you erase the symbol A and you write the symbol B instead, and you move one step to the right. We will design a tile like this. We will say, okay, you have to have QA on top and BR on the bottom. If you have a transition like this, QA goes to RPL, then you make tiles like this. On top, you put CQA for every C in the alphabet. And on the bottom, you put RCB. Okay, so you see that the A got rewritten to a B, and the thing moved one step to the left. And so now it's just in front of this letter C that used to be to its left before. And I don't know before what was on the left. So for every possible thing that could be on the left, I have to put in such a tile. Okay, that's pretty much the crucial steps we need. So now for every A in sigma, we make tiles of this form. Now you see why I insisted that there's a start tile. Otherwise, you'll just pick up this tile and say, yeah, I'm done. But of course, this is not a valid computation of anything. Okay, so this is the modified problem, but soon we'll fix it so that you can't just do this. Okay. And we're going to add 2 more special tiles. So one of them looks like this. Just hash mark on top and bottom. And the other one looks like this. Hash mark, and then the blank symbol with a hash mark. And finally, 3 more, which are what I'll call ending tiles. And these will allow you to kind of wrap up the computation at the end of the day. So what do they look like? So QA is the accept state of the Turing machine. So for every A in the alphabet, we'll put AQA, and in the bottom, QA. I see I made a typo in my notes, but I'll fix that after the lecture. Okay, so these things kind of allow you, when you reach the accept state, to swallow up the last few letters and complete the match. So those are kind of ending details. The interesting ones are the 2 tiles that force you to construct the next computation. So let's just do 1 step example of using these tiles. And I think this example will be more convincing than thousands of Greek letters. Okay, so supposing gamma, the tape alphabet for our Turing machine, has 0, 1, and 2, as well as the blank symbol and this. Yeah, that's it. Remember, the hash mark is not part of the alphabet. It's what we're using to describe computations. Let's say the word we start out with looks like this, 0100. Okay, let's say the first transition relevant in this case, it's reading the leftmost symbol, so it's going to be looking at 0, and it's going to be in the start state Q0. And let's say the transition said, go to Q7, erase the 0 and write the symbol 2, where the 0 used to be, and move 1 step to the right. Okay, so supposing that's the rule, that's the word, that's the alphabet. And let's see how the computation goes. So we start with our designated start tile. We have no choice. And the start tile looks like this. And that's it. Okay, so you look at this and you say, oh, Q00, I have to match that. Because right now I've only matched the hash mark on top. So what is the next thing to match is the Q. So you look for a tile that has Q00 on top. And sure enough, you find one, because according to this transition rule, we must have put in a tile that looks like that. Okay, so there's a Q00 on top, and there's a 2 Q7 on the bottom. Okay, so what have we matched so far? We've got this much matched so far. Okay, we matched it with that. And that, but now we've got a 2Q7 on the bottom. Sorry, I forgot one small detail. This should have had a hash mark here. Oops. And our special start tile should have been like that too. Okay. So here we are. We've got the Q0 matching with that. And now we say, all right, we have to match 100. Well, we have tiles for those things. Then we say, oh, we've got to match something with this hash mark at the end here. So we finally finished matching all these green things. But now what's left unmatched on the bottom? We have exactly this configuration, 2Q7100 plus plus the hash mark unmatched, which is exactly the next configuration. You see, this is very clever. So now you try to match this, you look for rules that will allow you to match it, and you'll find that when you finish matching it, what have you got on the bottom? The next configuration after that. Okay. And so now, when M enters an accept state, we might have, for example, something like this on the bottom. Uh-oh, my wonderful tablet has frozen. Okay, so when M enters an accept state, you might have something like this. So we use the tiles of this kind. AQA with a QA on the bottom and QAA with a QA on the bottom to catch up. Because now we don't want to generate a next computation, right? Or a next configuration. We're supposed to be stopping here. So we need to finish this matching. We use these special tiles for this purpose. And at the end, so this allows us to basically swallow up these letters, preserving the queue. And right at the end, we'll have swallowed them all up. We use this. So you use these two tiles. And you see everything now finally matches up and the computation is done. Okay, so these ending details are not so important. What's crucial was how we designed the tile so that a match with the extra string on the bottom produced the next configuration on the bottom after you finished matching on the top. But of course, this is not really the post correspondence problem. We now need to lift, we need to show how to lift the restriction of having a designated start tile. So basically this is easy. What you do is you design the tile such that you see right off the bat, if I don't use this tile, there's never going to be a match. And here's how we do it. Assume you have two symbols that you've not used before. And we'll call them asterisk and diamond. Okay, so never used them before. And then I'm going to define some operations on strings. So if u equals u0, u1 up to un is a string, maybe I'll put even a little vector sign on it. So u with the vector means string and the little u's means individual letters. Then this notation, star u is defined to mean put a star on the left of every letter. And this thing is defined to mean put a star to the right of every letter. You see, it doesn't start with a star, but it has a star to its right. Okay, so almost the same thing. Put a star to the left or put a star to the right. Okay. Now, for every tile, of the form some string t on top and some string b on the bottom, replace it with star T and P star. Okay, so there's just going to be this extra star offsetting it by 1. So if this is all that you had, you know right off the bat that you're absolutely screwed. There's never going to be a match because everything on top starts with a star and nothing on the bottom starts with a star. So no way are you going to ever have any match. So we put in one special tile. So we'll call that T0, B0, replaced with, so it's also been replaced with one of those star T0, B0 star, because you may have used that star tile in other places as well. But we'll do one special replacement. And for this one only, we will put in a tile like this. Sorry, not like that. Yeah, like that. So you see this one only, this is the only one that has a star on the bottom to start it. So I'll tell you, yeah, start however you want. I'm not putting restrictions, but you look at these tiles and you say, well, if I'm going to make a match, I have no hope if I don't start with that one. So you see, even though I haven't placed an official restriction on the rules, the design of the tiles forces you to start with that one anyway. So this, without loss of generality, we can say that you're working with the modified problem because you see that the modified problem can always be transformed into this one. And finally, to end, we'll add the tile star, diamond, and diamond. And after this, nothing can be added. Okay. So that's the end of the proof. So you may have gotten lost in details of fiddling with the tiles, but what did we do? We designed tiles in such a way that the only way you can get a match is by producing a valid computation of the Turing machine. Because the way the tiles were designed, it forced you, as you were doing the matching, to generate the next configuration. And when you hit the accept state, and only when you hit the accept state, I gave you special tiles to wrap it up. Okay, so now if you have an algorithm to solve instances of PCP, you can do this. You see this transformation was effective. I didn't really know in advance whether the Turing machine was going to accept this word or not, but I did know the rules, and all I needed to construct the set of tiles was the rules. So it's an effective construction of an instance of the post correspondence problem, right? i.e. a total computable function that transforms an instance of the acceptance problem into an instance of the post correspondence problem, together with the claim that the acceptance problem has a solution if and only if the post correspondence problem has a solution. And so our post correspondence solver should be able to solve the acceptance problem for Turing machines, but we know that's not possible. So there cannot be a solver for the post correspondence problem. This construction by post looks like a silly game, but it is absolutely way more useful than the halting problem. Because, shortly after the halting problem, people did a few things like this, but then these things proved to be way more useful for showing further other things were undecidable. And in fact, the post correspondence problem is one of the powerful ones that especially plays a role in mathematics way more than the halting problem does. But of course, the halting problem is kind of crucial because it got us started. That was the one we proved undecidable. without doing reductions and things. That was our grandfather of all undecidable problems. Okay, so we cruised through that faster than I thought. I have notes. There's a couple of typos in some places which I will fix later. But since I thought this might take us till noon, but obviously didn't. So I will pause and ask for questions, and then I will go diving into first order logic.
There are no questions on the chat.
Okay.
But I have a question.
You're allowed.
How, maybe I'm just not seeing it, but how do we know that the set of tiles is finite as restricted by the post?
Because there are only finitely many rules in the Turing machine and only finitely many letters in the alphabet.
Okay.
Everything about Turing machines is finite except their computations. This is the big difference between a program text and running a program, right? A program is always a finite thing. Even if it's a million lines of code, it's still finite. When you run it and it might go into an infinite loop, then it's no longer a finite thing. It's running forever. Okay. So I put notes on the website called Validity of First Order Logic is Undecidable. And I'm going to do that after the break. But what I'm going to do now is explain first order logic to you, which I imagine many of you know already. But in case you don't, here we go. First order logic. In contrast with higher order logic. Okay. So first, we will describe syntax. So there is a countable set of symbols called variables. There is a set, may or may not be finite. There is a set of symbols called constants. So for variables, we will just tend to use letters like X, Y, Z, U, V, W, and so on. For constants, we tend to use letters from the front of the alphabet. Okay, might be finite. Maybe our constants are A, B, C, or maybe there's just A, or maybe we're doing number theory and our constants are all the natural numbers. Okay, and then we have constants and variables. So now we have things called function symbols. There is a finite set of function symbols. These are not functions, but I'm going to call them function symbols. They only become functions when we interpret them. Right now, there's just no, they're just symbols. Associated with each function symbol is a natural number called its arity. Okay, and intuitively, this is kind of a primitive typing information. The arity of a function symbols tells you how many arguments it takes. And then finally, there is a finite set of predicate symbols. Each also has an arity. And again, just like the function symbols, the arity tells you how many arguments does this take. Sometimes we have a special symbol called this, which is always interpreted as equality. But I'll make that a parenthetical remark. We never take that symbol and say, oh, I think we use it to stand for plus now. The equality symbol is sacred. And when you use it, it has certain special rules that go with it. You actually get something called equational logic, which is another topic close to my heart, but I'm not going to tell you about equational logic. It's just there. Okay, now this is the starting point of the construction. So there are two types of things, or two kinds of entities. These are called terms, which stands for things. These terms designate things. Things are in the universe where your logic is talking about something. And then there's another entity called formulas. And these are statements. About statements, one can sensibly ask whether they are true or false. About things, it is absolutely meaningless to ask whether they are true or false. They're just the names of things. You don't say, is 3 true? You can ask, is it true that 3 equals 2 plus 1? That is a statement. Might be true, might be false. But 3 is not a formula. It's a term. It names a thing. And you might be wanting to say things about that thing. And that's what first order logic is set up to do, to define terms and then to say things about those terms. Okay, so I'm going to define the terms and the formulas inductively. So inductive definitions. So good examples to keep in, a good example to keep in your mind all the time is arithmetic. That's an example of a first order language. So we'll have variables n, m, so on that we typically use to write down statements in arithmetic. We have constants like 0, 1, 2, 3, 1, 7, 2, 9. We have function symbols like plus, which has arity 2, times, which has arity 2, minus, which has arity 2. And we could have ternary symbols as well. We have formulas like, sorry, we have predicates like greater than, or less than or equal to, or equal to. So number theory very much has equations in it, but also other things like inequations, but also other predicates like divides, which is a two-place predicate. So you can say n divides m. Is that true or not true? Might be true, might be not true, depending on what n and m are. Okay, so that should encapsulate in your mind the difference between terms and formulas. Okay, so inductive definition of formulas, of terms. 1, A constant is a term. A variable is a term. If f is a function symbol of arity n, and t1 through tn are terms. So you see this is an inductive definition. Once you construct some terms, you can use this induction to construct more terms, and then you get more terms. And when you do this for omega steps, you've got all the terms. So if this has arity n and t1 through tn are terms that you've already constructed, perhaps starting from the base case, but maybe you're way up in the construction already and you've already built up some complex terms, you can build up yet more complex terms. Then f with these things stuck in this is also a term. So formulas. So this is terms, and now formulas. If T1 and T2 are terms, so you have to construct the terms first, because otherwise you don't have anything you're talking about. If T1 and T2 are terms, then T1 equals T2 is a formula. If P is a predicate symbol of arity n, and T1 through Tn are terms, then P of T1 through Tn is a formula. So the predicates apply to terms. They make statements about the terms. All this thing that I'm saying that's interpretational is in the background. In the formal definition of the syntax, there is no interpretation. I'm just building these things up according to rules with no interpretation. If phi is a formula, so if phi is a meta variable that I'm using in my language to describe the language of logic, phi is not a symbol of the logic itself. It's a meta-logical symbol. So if phi is a formula that you've already constructed, then not phi is a formula. So all the Boolean connectives can now be applied. If phi1 and phi2 are formulas, then phi1 and phi2, phi1 or phi2, phi1 implies phi2 are formulas. So we'd already seen these guys when we talked about propositional logic. Okay, so this is first order logic. This is not modal logic. So definitely no modal stuff here. But we have this a thing that we didn't have in the modal case or in the propositional case. We had variables, and they appear now. Phi is a formula, and x is a variable. Then for all x phi and exists x phi are formulas. So a formula does not mean anything. Until I specify an interpretation. So I informally said formulas are things that could be true or false, but actually they can't be any such thing until I tell you what they mean. And the crucial point here is that I have many different sensible interpretations. So when I was using the example of number theory, one of the bad things about that example is that it has a very familiar interpretation that we all have in mind. Right? We certainly know arithmetic. We know what plus means. So these are not uninterpreted symbols in our head. And by giving you that particular examples, you might have thought that these things come with a natural fixed interpretation. This is far from the case. The interpretation is something we cook up, and we can make completely different interpretations for the same symbols, with the same function symbols, and the same predicate symbols, but totally different interpretations. Even with arithmetic, we can do that, because we can say, oh, I'm now going to interpret everything mod 17 instead of making it ordinary arithmetic. And that's another completely different, equally sensible interpretation of the symbols of number theory. So we have this flexibility to cook up interpretations, and we are going to specify exactly what that means now. So an interpretation. So we assume we have a set D called a domain of discourse. Informally, this is what we are talking about. Okay, so we decide today we're using this particular language to talk about natural numbers. Tomorrow we're using it to talk about matrices. The day after we're talking about some random commutative ring. Completely different things, maybe, but we're using the same language perhaps in all these different settings. All right, so D is what we're talking about. We always use this letter D. So an interpretation which I'll write with this fancy script I symbol, consists of three things. One, for each constant symbol, A, we have an element D sub A in D. A is just a symbol. By itself, it means nothing. But now I'm saying, this A, now in this context, I'm using it to stand for a particular element of this concrete set D. Okay, so we can't write A belongs to D because A is just a notation. All right, then for each function symbol, f of arity n, we define a function. You notice the difference between function symbol, that's just notation with no interpretation, and function, which is a real live function, which I'll call f sub d to distinguish it from the symbol f. So this d kind of tells you I'm interpreting f now. And what kind of thing is it? It takes n elements from my domain and interprets it and computes some new element in my domain. That's what functions do. They take inputs and they tell you an output. Okay, so this is a bona fide live set theoretic function as we've always known and loved, and it is now the interpretation of our uninterpreted, hitherto uninterpreted symbol f. For each predicate symbol P of arity n, we define a subset So now we're interpreting what this predicate means. And how do we interpret it? We say, you have this property, you have this property, you don't have this property. So the guys who have the property, we collect them into a subset. And that subset is basically defining what the predicate means. So we define a subset, which I can call P sub D, which is a subset of n tuples. Why n tuples? Because it's an n place predicate. If it's a unary predicate, it'll simply be a subset of D. If it's a binary predicate, it'll simply be a subset of D cross D, and so on. So we're going to use this notation to stand for the interpretation of. So the interpretation of A is this element D sub A. Now, what about the interpretation of a variable? Well, gosh, now I don't know. This is like asking me in number theory, hey, is n positive? And I go, well, what is n? Meaningless question, right? You have to give me a context in which the question makes sense. So we need to provide a context. So this context is called an environment. You may be familiar with this term from programming languages. An environment is a map from variables, we use the Greek letter rho, from variables into D. And this describes the context. It says, now I'm in the context where the variable symbol X stands for the element, I don't know, 23 in our domain of natural numbers. So now we have to revise everything. So we have to say a constant interpreted in an environment rho is D sub A, because actually it ignores the environment. Constant means constant. It doesn't depend on things that you assign to the variables. But if you ask me what does a variable mean, then I need to look it up. And how do I look it up? Well, rho is a function. I just apply it to X. It's precisely telling me for every variable, which element in D am I talking about. And now the last thing. To interpret a generic term, I take the interpretation of the function f. Now this function symbol f, and I interpret each one of those terms. Okay, so now The square brackets f thing is a bona fide function, no longer just a mere symbol. The t's have been interpreted. So again, you see this is an inductive definition of the interpretation of terms. Okay, so now formulas have truth values relative to an interpretation. So an interpretation, so I'll write script I for the interpretation and rho for the environment, because I need the environment as well. And then I'll say this formula, this means satisfies. So this interpretation satisfies this formula if this formula turns out to be true. So I'm specifying what truth means. So I'll say this thing is equal if the interpretation of T1 actually equals the interpretation of T2. So this is the equality symbol in my first order logic. This is my meta equality. This is identity of elements in D. Similarly, I'll say my interpretation and environment satisfies this predicate T1 through Tn if I look at this tuple, which is the interpretation of all the terms, and it turns out to be in the interpretation of P. Okay, I'm going to use this notation to mean an environment in which X denotes D. So now the truth of Boolean combinations is exactly what we did in propositional logic. So let me explain the quantifiers. So we'll say an interpretation and an environment satisfies an existentially quantified formula if for some D in D, the interpretation of rho, but now rho updated with X bound to this value D, satisfies phi. And analogously for the universally quantified formula. So that's what interpretation means. So now, this was meant to be kind of a recap of things you know. So given a formula, three things can happen. One, phi could be true in every possible interpretation. That's one thing that might happen. Second thing that might happen, phi could be true in some interpretations and false in others. And three, phi could be false in every interpretation. Okay, good. So if one holds, we'll say phi is valid. So unlike in propositional calculus, where the only concept is true or false, in situation 2, we'll say phi is satisfiable. In situation 3, we'll say phi is unsatisfiable. The opposite of valid is not the same thing as unsatisfiable. The opposite of valid means could be unsatisfiable, could be satisfiable. Okay. All right. So this is the question that we are interested in. So all this studying what things are valid, what things are true, and what interpretations, all this is a branch of logic called model theory. And in fact, we will sometimes say I rho phi. We sometimes say phi is, sorry, we say I and rho is a model of the formula phi. Okay, so let me introduce, there's another concept called proof theory. So you see, I use the double turnstile here. This is all about building models and looking at the concept of truth. Proof theory is based on proving formulas starting from axioms and using rules. And one important thing to keep in mind is that these are completely different things. People just absolutely confound them. And the reason they confound them is because they're closely linked, but not definitionally. They turn out to be closely linked. So let me just tell you what that link is. So this notation means starting from assumptions in gamma, I can prove phi. Okay, so this is all about provability. You have to write down what your rules of inference are, what your axioms are. So now you have what's called a proof system, and then you can go around proving things. And ultimately, you can prove some formulas that don't depend on any assumptions. So then we have a situation like this. That means phi can be proven regardless of any assumptions. Unconditionally provable. Notice I'm carefully not saying true, because proof theory is not about truth, it's about provability. Okay, so we call such a formula phi is a theorem, something that you can prove. Now, why do we confuse these concepts of proof and truth so much? It's because we have two grand theorems. In reality, we're interested in both, because the proof theory tells us what things we can establish through our rules. And what model theory tells us is, what the hell are you talking about? It gives us some content to what we've been proving. So soundness says, sorry, one more. Yeah, soundness says this. If phi is a theorem, then phi is valid. So let me make a stronger notion. So we'll write it like this. Phi is valid. Okay. This means true in any interpretation. And I'll make this notation means any interpretation such that all formulas in gamma are true. Now I can talk about truth. Forces phi to be true as well. So the soundness theorem can actually be boosted up. It says, if I've got a proof system and using some hypotheses, I was able to prove phi, then it's true that any interpretation which makes all the formulas of gamma true will automatically force phi to be true. So your proof system is actually telling you true things. That's nice. There's some connection between the formal game we are playing with proofs and the interpretation we're interested in deeply understanding. But we have a much better theorem as well. If something is true in all interpretations, then it's provable. That means your proof system that you've cooked up with has enough power to prove everything that you might be interested in. So not every logic has this property. So first order logic has a complete proof system. Many of the modal logics that we've studied have complete proof systems. However, there is no complete proof system for number theory. And this is basically the content of Gödel's incompleteness theorem. By the way, Gödel also proved the completeness theorem for first order logic. Okay, but we're not here to talk about completeness. We're here to talk about validity. And the theorem that I'm going to prove after the break is the set of valid formulas of first order logic is undecidable, but is CE. It is computably enumerable. And how are we going to do this? We're going to show that if we had a gadget that could solve the validity problem, namely you give it a formula and ask, is this valid or not? If we had a gadget like that that could answer that, it could also solve the post correspondence problem. And we know if we could do that, we can solve the halting problem. So now you see we're getting 2 steps away from the halting problem to prove undecidability. I will stop we'll take a break now. Yeah. And then there is something called screen share, isn't there? Oh yeah, here we go. Yes. Okay. Now, so what have we done so far today? We've done 2 things. We just did a crazy reduction that shows this apparently cooked up little game is undecidable, the post correspondence problem. And then we talked at length about the notion of validity. So now I'm going to prove that validity is undecidable, okay, by showing that the post correspondence problem can be reduced to validity. It's indeed going to be a mapping reduction. Okay, so here's how we go. So I'm allowed to cook up a very special formula. And here's how it goes. So this, what do we have? 35 minutes. Yes, let me try and do all this in 35 minutes. Okay, so our alphabet is going to be 0, 1. Okay, so in our logical formulas, we will have 2 function symbols, which we will call f sub 0 and f sub 1. And it's not a coincidence that these are exactly the letters in our alphabet. And 1 constant, which I'll just call A. Okay. Now, suppose W is a word over 0, 1. So let's say W looks like this, W1, W2, up to WK. Each WI is one of these letters, 0, 1. Then I'm going to write FW sub A is shorthand for FW sub K applied to FW sub K minus 1, F1A. Okay, so for example, if my word is 0, 1, 0, then f sub 0, 1, 0, a is shorthand for f of 0, of f of 1, of f of 0, of a. 1, 2, 3. 1, 2, 3, 1, 2, 3. There we go. So everybody get the idea? This is the official notation, putting functions together. But the point is now I can build a term that encodes a word. And the A is just there as an end marker to kind of signify, to give the first F something to be applied to. So these Fs are all unary function symbols. Okay, so 2 unary function symbols, 1 constant, that's it. Build the terms. So what do the terms look like? Is, F0, F1, F1, F0, ultimately ending in A. So the only thing that it's encoding is a word. So the term encodes a word. And now you can see that's going to mediate the passage from thinking about strings to thinking about terms in our logic. All right. Now we're going to, that's the term part of the language. There'll be a single binary predicate P. Binary, so I'm showing it with 2 holes that I can put terms into, and P will either be satisfied or not. Right, ready? Okay, good. So suppose we have an instance of PCP. So what does such an instance look like? And of course, I mean over this alphabet that I've already spelled out, namely 0, 1. So our instance of PCP looks like this. There's an alpha 1, beta 1. There's an alpha 2, beta 2. And there's an alpha n, beta n. Okay, alpha, beta, these are all pairs of strings. Each of this is a pair of strings. You should think of this as a little tile with the alpha written on top and the beta written down below. We are going to code up the description of a tile in a formula. That's how it's going to work. Okay, so let me just write down a massive formula, and then we will try to deconstruct it and spell out what it means. But at first it'll just look like a monstrous thing that's spanning the page. So there's going to be a big conjunction, I going from 1 to n. What's n? The same n that's in there in the PCP. So for every kind of tile, there's going to be one conjunct. And this formula says P holds for f of alpha I applied to A and f of beta I applied to A, where I'm using the abbreviation I've introduced above, where f of alpha I is a string, so it's interpreted through all those cascaded unary function applications. Okay, just it. What is P? I'm not telling you. It's just a predicate I've introduced. I'm saying this, well, would it be if that was all there was to it? But it's not. And, okay, so let me be liberal with my use of parentheses. So all this and now, for all x, for all y, big square brackets, P of xy implies big conjunction, again going from 1 to n, P of f of alpha I applied to x f of beta I applied to y. That closes there. And then that closes that square bracket. And then let me put a curly bracket around this whole thing. All this together implies there exists z p of z z. Just a formula I pulled out of thin air. Okay. But of course, as you can see, it was constructed from the instance of PCP that I was given. Okay. What we're going to prove is this formula is valid if and only if the PCP has a solution. But first, note that the translation from the PCP instance to the logical formula is certainly a total computable function. I've explicitly shown you how to do it. This is not some vague, there exists a formula, blah, blah argument. I've written down, this is the formula. And this formula is valid if and only if the PCP has a solution. But to understand this proof, let's try and intuitively understand what this formula is trying to say, which is of course not the same thing as the formal interpretation. That will come later. But let's just intuitively see what was the thinking behind putting this formula down. So the way you should think about this PXY means by putting dominoes together or domino tiles together, you can get X on top and Y on the bottom. So if PXY holds for two strings X and Y, it means exactly that somehow I found some combination of dominoes that produces, when I concatenate all the top strings together, I get X, and when I concatenate all the bottom strings together, I get Y. It doesn't say that X is equal to Y. Of course, it doesn't say that. It just says I put some strings together and I got some strings. All right, clear? Good. So let's see, why does it say that? Let's see what the first thing says. Look at what this thing is saying. This is nothing but a description of one tile, because it's saying, oh, P holds if I've got alpha I on top and beta I on the bottom. And what's alpha I and beta I? That's exactly one of the tiles that I've been given. So just unconditionally asserting that. It's saying for each one of the possible tiles, I'm just telling you, it's possible to take that tile and then you'll get alpha I on top and beta I on the bottom. So I'm just asserting P holds of F of alpha, F sub alpha I of A and F sub beta I of B. So if this is not clear, you have to stop me now. Yes, it's clear that this thing is saying that. Okay, now look at what this thing is saying. It's saying for any X and Y, if somehow you've managed to put tiles together and get X on top and Y on the bottom, then you can extend that to a longer thing, which will give you alpha IX on top and beta IY on the bottom. Simply by adding the appropriate tile to what you already had. At no stage did I say that the strings were equal. So this whole thing in curly brackets is encoding the description of the post correspondence problem. It tells you what are the basic tiles I've got. That's what this thing underlined in red does. It just says you've got these tiles. So you can just start with any of them. And then it says once you've got some bunch of tiles already stacked up, you can choose any tile and extend it. That's all it's saying. And these are the rules of the PCP. You've got all these tiles. You can take anything that you want and stack them up however you want. And this whole thing just says That's the PCP that you're working with. What does it imply? There exists some way of getting Z on top and on the bottom. So the consequence of this is, yeah, I've got a match. So this whole formula is saying the formula is basically saying this PCP has a match. Okay. So let's see. So actually this thing that I said is the intuition is almost a formal proof. So first direction, assume formula is valid. Okay. That means true in any interpretation. Any. So I can cook up an interpretation that suits my purposes. All right. So I can cook up an interpretation. So the domain of this interpretation is strings. All right. Now I have to interpret my symbols. The interpretation of this constant is empty string. Interpretation of f sub 0 so this is supposed to be a map from strings to strings. It's unary, right? So it takes a word W and it sticks a 0 at the end of it. The interpretation of F1 is a function from strings to strings because strings is my domain. So it says, give me a word, I will stick 1 at the end of it. And then interpretation of P is, it's got to be a set of pairs, right? So it's the set of all pairs of strings, alpha I1, alpha I2, alpha IK, beta I1, beta I2, beta IK, such that for some sequence of integers, I1 through IK. In short, P is exactly the pairs of strings that I can get by putting dominoes together. I just formalize it. That's what I said intuitively. Now I'm saying it. I'm saying the same thing with a bit more Greek letters. Okay, so this just formalizes what I've been saying all along. So since the formula is valid, it is true in this under this interpretation. Okay. Now, of course, what is this formula? It has the structure of an implication. The antecedents are clearly true of the implication are clearly true. I mean, if you look at how P got interpreted, and then you look back at what was being said in that antecedent, it's exactly saying, hey, the things in P are like this. Okay, so the antecedents of the implication are clearly true. So exists Z, P, Z, Z has to be true, i.e. PCP has a match. So it's just cleverly coding up everything on the PCP in the logical apparatus. Not even that much was needed. Other direction. Assume PCP has a solution. Need to show the formula is valid. Okay. Again, we now are getting to assume that the PCP has a solution. Okay. Now, showing validity of this formula, of course, we can't say that we hacked the interpretation to our needs, because it says whatever you interpret, however you interpret it, it better be true. All right, so we're going to do that. But we have this powerful assumption, namely that the PCP, which is used, which is baked into the construction of this formula, that PCP really does have a solution. And so now we have to argue, regardless of how you interpret uh, the F's and the P's and so on. So regardless of how F0, F1, A, and P are interpreted, we can prove by induction that if the antecedent of the implication holds, so remember, what we're trying to prove valid is a great big implication. And I need to keep reminding people of this. But what does it mean to prove a great big implication? Well, the contract is you get to assume all this. Everything here before the implication, everything before that you get to assume. And that you get to use as your toolkit to try and prove the thing that follows. Okay, so all this is in our toolkit. We know these things are true. How do I know those things are true? That's what if means. So we can easily prove by induction then if we have any sequence of k integers in the range 1 to n. So let's say these integers are called j sub 1 to j sub k, that p of alpha j sub 1, alpha j sub 2, up to alpha j sub k, comma, beta j sub 1, beta j sub 2, beta j sub k holds. What am I doing? Induction on the length of this sequence. What's the base case? K is 1. K is 1 means I've got only one thing in my sequence. So P of alpha j, beta j holds for any of those integers in the range. And by golly, that is exactly what the first clause of my assumption tells me anyway. Then proceeding with the induction, it says, oh, well, supposing you've constructed this for a sequence of length k, you somehow figure out that that holds. I'm going to argue that now if I put another alpha beta pair on it, that will still hold. And by golly, this is exactly what this guy says anyway. Not, this is the easiest induction you've done in your life. Okay, so we've just said P, this holds. Very good. So all this follows from the antecedents, but now we have to prove that PZZ holds for some Z. But we assumed that the PCP had a solution. Yes, we assumed that the PCP had a solution. So the sequence of integers defining that solution will produce the string Z on top and bottom. And by our little inductive proof, PZZ holds. There you are. So here we didn't make any assumptions about how we were interpreting things. We just said, doesn't matter how you're interpreting it, the logical formula has already baked in induction into it. So this holds for anything that I can construct from the PCP. And then the PCP solution assumption is, but there is the solution that actually produces the same thing on the top and the bottom. That's exactly what exists Z PZZ means. So if the PCP is actually got the solution, this formula certainly is valid. And that is the end of our proof. So validity is undecidable. So this is a sad blow for those people who came up with programming languages based on resolution-based theorem proving, because forget it, it's not going to work in all cases. But it works sometimes, and when it does great stuff. But it's not going to be decidable to show that formulas are valid. But notice I did say it's RE. Why is validity RE? Oh, sorry, CE, modern terminology. So there is a Turing machine that will spit out all the valid formulas. And you can sit around waiting for your favorite valid formula to show up. And if it shows up, you'll go, yay, it's valid. But if it doesn't show up, you don't know. Maybe if I wait longer, it'll show up. Right? So it's a semi-decidable thing. So it's not hopeless. So how do you do this? So completeness tells us if a formula is valid, formula is valid if and only if it is a theorem. Right? So there are proof systems for first order logic that guarantee properties like this. So instead of searching for validity directly by constructing models or whatever, you search for proofs. So systematically enumerate proofs. And every time you complete the proof construction, output the formula. And because of this completeness theorem, any valid formula, well, one day you'll find a proof for it, and it will be output. But this thing will never tell you, by the way, this thing is not valid. It will only say, so far, I haven't found a proof. Sometimes people get desperate and say, maybe this thing is, undecidable. People are starting to say things like that about NP completeness. About P equals NP, they're thinking, oh, maybe this is not a well-defined problem. That's just a sign of desperation. But anyway, so here's the deal. First order logic is undecidable, but the proofs are recursively enumerable. And hence validity is recursively enumerable. You might wonder, why did we call this first order logic? What's second order logic? So quantifiers only range over individuals. In first order logic, not over functions or predicates. Remember we said you have some fixed set of functions and that's it, and you interpret them and then you work with them. You can say for all x blah blah blah, but you can't say for all functions something or the other, for all predicates something or the other. Wait a minute, didn't we say that once? Well, that's the principle of induction. It's a second order formula, because it says for all predicates blah 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 blah, induction holds if and only if well-foundedness. So if you're quantifying over predicates, you have second order logic. Quantify over function symbols or functions and predicates. And this is not even RE. Sorry, I keep saying the old language, not even CE. Certainly undecidable, of course, because first order logic is a fragment of it. But bizarrely, if you look at monadic second order logic, so this is, you have second order quantifiers, but only over unary predicates and not over function symbols. It says, yeah, it'll be just like first order logic, but I will allow you to write quantifiers over monadic predicates only, no quantifiers over functions, no quantifiers over binary predicates. Monadic means one argument. Only over unary predicates. So this is kind of a fragment of second order logic. And this fragment includes most modal logics. And indeed, monadic second order logic is back to being decidable. So this was a shock because people by this time knew that first order logic is undecidable. How the heck can second order logic be decidable? But it was monadic second order logic. So it's not a proper extension of first order logic. It's like the only quantifiers I'm allowing you are these monadic second order quantifiers. Okay. And in fact, the whole theory of omega automata was invented by Bucci as an attempt to prove this theorem about decidability of monadic second order logic. He made the connection between Bucci automata and monadic second order logic. They correspond perfectly, in fact. And he proved, and then of course the complexity people got into the act and they proved that the decision procedure for monadic second order logic is non-elementary. Does everybody know this word non-elementary? Maybe I should use an existential quantifier. Is there anyone who doesn't know what this word means?
No. Well, like
There's nobody who doesn't know what it means?
there's people that don't know what it means.
Right. Okay, so let me tell you. So the running time is not bounded by any finite stack of exponentiations. So, you know, big O of 2 to the n, we call this exponential time. Big O of 2 to the 2 to the n, we call this double exponential. Then you say, well, I'm letting you stack like that. That's like a stacked exponential. So non-elementary means it goes beyond any stacked exponential. Okay, so there's no finite stack height that you can impose that will give you a bunch of exponentials that bounds the running time of the decision procedure for monadic second order logic. Okay, so non-elementary means beyond any stacked exponential. Okay, with that, I leave you and end this lecture. I will hang around to chat if anybody is interested. Let me stop sharing. And let me stop